this Medallica notebook, or this Medallica model, exists in order to explain the difference between two separate or kind of oddly similarly worded but very different applications of the Z transform, or of the idea of a Z transform transfer function. And so just to be clear, I've tried to be a little bit clear here with these colors. So what we're doing is we have a particular input into the system. We're taking that system. Well, I've used a bit of a convention here to, I've made the continuous signals continuous lines and the discrete signals dashed lines so that we can tell the difference. On this diagram, this is just my own convention. It's not a standard convention. And we can see that we have two different kinds of problems. So we have an approximation problem, and we have the problem of finding a sampled equivalent. And from the diagram, I want to first kind of be clear on how this is different. So in the first case, we have a first order system, and the input to the system and the output from the system are both continuous. So in the first case, we just have a continuous input going into a continuous transfer function, and everybody should be able to predict what that result is like. In the second case, we now ask the question, what if I wanted to replace that first order system with a set of discrete machinery such that the relationship between this red line and this approximated line is near to one another, or so that these two blue lines are similar to each other, right? So I want to build an approximation of this first order system, which could take any continuous signal, right? So I'm not just constrained here by having a ramp. I want to have something that has similar properties whether I have a ramp input, or whether I have a step input, or whether I have a sinusoidal input, any kind of input that I can think of. I want the light blue line to approximate the blue line. And this is the question. In other words, given a continuous transfer function, find an approximate transfer function that would behave similarly to that continuous transfer function. That's the question. The answer is discrete approximation, and the only method that I expect you to know for discrete approximation is the backward difference approximation, right? And one very important thing that I also want to make clear is that I do not expect you, I never want you to use the backward difference approximation if we have known input signals and known output signals, and our task is to find a discretized version, or the Z transform of a sampled version of this output. In that case, we always use the exact discretization using the data sheet. Right, so I can discretize this signal, and I can obtain a Z transform for that discrete signal over there. And I can also discretize the response of that system to that signal. And I can get an exact discretization of that signal. And that is a different problem from finding the discrete approximation of a continuous transfer function. The reason why it's different is the discrete version of that eventual output, if I know the input, will typically depend on both the input and the output. In other words, I can only typically get an exact output if I know the actual continuous signal. And in most cases, I am unable to find a discrete system that behaves exactly like the continuous system. Is that clear to everybody? Does everybody understand that basic idea, that this is like something that is not possible? In other words, in general, we cannot build a discrete system which behaves exactly like a continuous system. with a finite step size, because we'll always, at the very least, we'll always be a time step behind, right? Because we're sampling. So even if we knew some magic formula that could do it, we couldn't get over the fact that like the machinery itself takes time to run. And so we would, at the very least, we'll be behind. And so people get confused because they imagine that if I take this signal and I multiply it by that transfer function continuously, this function of S, which I can find, which you all can find, this function of S, which I can find, if I multiply those together, I get a function of S there, and I can inverse that Laplace transform and get an exact representation of that signal. Now what I can also do is I can get the exact Z transform of what would happen if I were to sample this signal. And all of those things go through the table in the datasheet, right? When I do this, when I ask this question differently, when I say, I want to build a discrete machine that behaves similarly to that thing, to an arbitrary input, that's when I use backward difference, right? Then I have this whole other problem. I have a whole other hypothetical situation, which says, let's assume that I still have that actual system in place. Let's, for instance, assume that that continuous system is a plant or a tank, an actual continuous piece of equipment. What if I wanted to interface with that continuous piece of equipment from a digital system? I would need to include a hold element in front of the system, right? And that system, in order to make sense of that continuous system's output, would need to sample the output. And now I can ask, what would it, from the point of view of the digital system, what would that continuous system's transfer function be in the digital domain? And here, because we're introducing the sample and hold, the response of that system to a signal, some continuous sample, which is some continuous input which is sampled and held, will be different to the response of the original system to the original continuous input. Again, because at the very least it'll be delayed, but also the sampling equipment introduces variations. If in the case of a zero order hold, it makes whatever input we had, whatever smooth input we had, into this kind of combination of steps. And so what we'll see in the output is a combination of steps. And what is recorded in table 17.1 is the equivalent transfer function for this block diagram that we have over here. And so I just want to show you, I went back and just kind of looked at the textbook myself, and didn't trust you guys to do it for me, but when I did the calculations myself, it does actually work out exactly the way that you expect. Let me just open this stuff up. So here we have the ramp input and the so that's the ramp input that we got there, and here is the continuous output. Now, unfortunately, I'm trying to figure out why this hasn't saved the beautiful plotting that I made. Here's one that I prepared earlier. But you can see, I'll just show it on this one so that I can reveal the stuff like I go on. So here we have that, so that's the ramp input, right? And we see that the continuous system has what we expect, a nice continuous response to that. Now we can say, what if we wanted to approximate that? And the approximate here is what's coming out of zero order hold 1. And so that first zero order hold, that output over there, what I want to draw your attention to is this is not a sampled version of that output. It is an approximate version of that output, but with a sampled signal. So it's going a little bit above and a little bit below. It is not coinciding exactly with the continuous result. Yes?
If you had the analytic solution to that continuous output and you just do a Z transform of that.
Yes. And they would line up exactly.
Yeah, and so you could divide the input Z transform and the output Z transform to get an exact representation. With that, G of Z holds for any type of input?
No.
Just for that specific?
No, and it's important that you understand why, because there is no sampled version of y going into that system. There is no transfer function that I can identify between, so in other words, if I sample this input and I sample that output, there is no discrete transfer function in that sense that relates these two to one another, because those are continuous signals going to continuous signals. It's a quirk of the discrete domain that not every discrete system has a transfer function representation. Now, I just want to say that again because I think a lot of people are thinking like, how could that possibly be? Remember that the transfer function notation only works if I can separate out the input and output from the machinery of the system. And in this case, that would not be possible. So I could find the continuous transfer function and I could inverse that Laplace, right? But it would be incorrect to say that anything in the system is actually responding to the sampled version of that signal. Is that making sense? Okay. I'm gonna run through this and then I'm gonna turn off the recording and go to the board, and then I'll try to run through this again. It's a weird concept because you have an expectation, like you think that there should be a transfer function, but you forget again what transfer functions are, like how special linear systems are. So I'll explain to you why this isn't possible. But let's just run through this quickly again. So we've got an approximate, this is why I've made that color different. Right, so this line and that line are not the same. We're trying to get them the same, and in general they will become closer to one another as the step size reduces. But they are not ever going to be analytically exact. Okay? It's an approximation. Here, because we have this stepwise input going into that sampled signal, it is actually possible to find out exactly, to find a transfer function. Another way of explaining this to yourself is that there is actually a discrete system there. In other words, there is actually a sampled version. This box over there, the gray box that I'm selecting there, is a discrete system. In other words, it has a discrete input and a discrete output. Okay? And it is a discrete machine. In other words, it's doing things in a discrete kind of way to its inputs. And so we can find a discrete transfer function there. If you want to remember, if you're into kind of just memorizing rules, because I know the logic is weird to follow, but basically you can only get a transfer function between a discrete signal and a discrete signal if there's a discrete signal entering the box and a discrete signal exiting the box. And that's to a certain extent an explanation of why you can't get a discrete transfer function here. Right? Because the box is over there. In this case, you have a continuous signal on the one hand, and you have a discrete signal on the other side, or a continuous signal on the other side. And you can't get a discrete transfer function that relates those things because there aren't discrete signals coming in and discrete signals coming out. Okay, so at best, you can get something that is close. And this is exactly what we see. When we actually plot this, we see that that's the output that we expect over there. Over here, look at what's happening over here. We've got the same transfer function in the sense that it's the same tank. We have a hold element in front of it. And what this means is instead of smoothly moving, so let's think about why wouldn't we be able to predict what's happening to a continuous system using only the values that are at the sampling points? And the obvious answer is because we don't know what's happening between the sampling points, right? Because a lot of input signals have the same Z transform. And so fundamentally, you can imagine that if, so you think, oh, okay, I know this is the ramp that goes into that signal, right? I know that there's a ramp coming in. But from a Z transform point of view, by the time I've sampled this signal, right, I just have the values at the sampling points. And so fundamentally, I don't know, the machine doesn't know whether the input actually did this. Right? Now, under some very strict assumptions about exactly how the reconstruction works, so for instance, the one that I expect you to know is this particular one, which is, oh, I know what happened between the sampling points, nothing. Right? Everything just stayed exactly the way they were between the sampling points. Under those conditions, it's easy to predict how the system will respond because I'm just predicting that the system will do little step responses. And I can find, in most cases, the analytic step response after a certain amount of time, and that's the discrete response. And that is exactly what the approach that's taken in table 17.1. Yes? There's no error. So this discrete transfer function has 100% exactly the same response as the discrete transfer function that goes between this sample signal and that eventual sample signal, yes. So these are exactly the same. And let me show you what that looks like. So these systems are sampler 3 and transfer function 2. And so if I enable those, so that's sampler 3, and that's transfer function 2. And what you can see, I mean, it's not easy to see, but what is happening, the reason why the scale is changing is just because that, let me just hide that over here. So that's sampler 1, transfer function, right? They are identical to each other. And the continuous transfer function that we're talking about here is first order 2. So what right? So what we can see is that that first order system is describing these step responses to the sampled signal that's coming in, sampled and held system. And the discrete system is corresponding 100% exactly to the continuous system at the sampling point. And that's basically what table 17.1 is giving you.